it is immediately clear that P is equivalent to itself. So we just need to show that it's a martingale measure. That is, that the discounted risky asset price is a martingale under P. So, three things a martingale needs to satisfy. First, integrability. Well, the initial value of the risky asset is finite almost surely. In fact, it's constant, it's finite just for all omega. And at time step 1, the value of S1 is given by S0 multiplied by this exponential factor, which is, of course, positive because it's exponential, so the absolute value disappears, and which we can write more explicitly because we know that x is a standard normal random variable. So it has a density, and we can use knowledge of that density so density means that we have the expectation is the integral over the state space of the function of just now little x against the density of the process of the random variable, which here is the density of a standard normal. Combining these two, we get some nice cancellation in the powers and end up with 1 over square root of 2 pi e to the minus x minus sigma squared over 2 dx. This, oops, too far, is the density of a normal random variable with mean sigma. And so integrating over the entire density, because it's a probability density, is going to be equal to 1. So this whole thing is, this integral goes to 1, and we get S0, which is the value of that risky asset at time 0, which is, of course, also less than infinity. That's what we had to prove. And we've ended up inadvertently proving the martingale property anyway. So that's integrability. It's also the martingale property. Because S1 is almost surely positive, expectation with absolute value or without is the same. And conditioning on F0 doesn't make a difference because F0 is the trivial sigma algebra. So that's the martingale property. Adapted is clear because the risky asset was always adapted to the filtration. That's part of our assumptions. And so P is an equivalent martingale measure. Now for part B, we want to deduce a formula for the price of the option. Which is the expected value of that option. Well, we can just plug in what we know to be the value of S1. So this is now little S0 exactly as we saw before. In the same way, we could write this expectation as an integral because the only random object in this expectation now is the random variable x. So we have the function multiplied by the density of the random variable. We could do some substitution here because this function is only going to be positive. It'll be 0 for any values of x which send this object on the left to be smaller than k. That's how the plus works, right? It's taking just the positive part. So we can actually integrate only from a certain value, which we shall denote by capital T. leave everything inside the same for now, where t is a value of x such that S naught e sigma x minus sigma squared over 2 is equal to k, because that on the left hand side is increasing with x, so when it's equal to k, that will be the point at which it starts becoming positive, right? So sorry, that value of x is that t there, and rearranging gives us that t is equal to 1 over sigma log k minus log s naught plus sigma over 2. Now the thing on the inside we've ensured is just positive, right, for all time. We don't need that plus anymore. So we can split the two integrals, so this is going to be useful. Split this thing here using linearity of the integral. On one side, something that actually we've already seen in part A, how this is going to cancel very nicely. And on the other side, k, now with no extra factor, just the density of the standard normal random variable. We can simplify the left-hand side and even use a substitution to get it in the same form. So that's just exactly as we did in part A. And the right-hand side, for the moment, stays the same. Okay, so we've got a difference of two integrals over the standard normal density, but on different integral limits. Nevertheless, we can write these in terms of the standard normal cumulative distribution function, which on the problem sheet is denoted by capital phi. That should be little s naught, but of course actually it doesn't matter. This on the left hand side is 1 minus the cumulative distribution function of t minus sigma. 1 minus because the cumulative distribution function integrates from minus infinity up to a value. And here on the right hand side something similar, but just with t and not with t minus sigma. All that remains to do is notice that from the choice of our function t, not the function, the value t, 1 minus phi of t minus sigma is going to be equal to phi of d plus as defined in the lecture notes. No, sorry, not the lecture notes. On the problem, the exercise sheet, and 1 minus phi t to be equal to phi of d minus as defined in the exercise. And so we've proven what we wanted to prove.